did last time. We had we looked at the Penrose diagram for Minkowski space in electromagnetism, and we noticed there was a matching condition which said that the radial component of the electric field at scribe, the bottom of scribe plus, is equal to the radial component of the electric field at the top of scribe minus, where there's an anticimal map here which I've hidden in my choice coordinates, which have the property that z at scribe minus is going, at scribe plus is going to the integral point scribe minus. And then from that, it immediately follows that we have conserved charges, scribe plus minus, that are numbers that can be computed classically, which are the same. They're generically non-zero, and they're the same whether you compute them on scribe plus or scribe minus. And this is a relationship between quantities evaluated and computed out here, but we can turn it into a much more non-trivial looking relationship just simply by using the Gauss law, and we get an interesting relationship between the charged, infinite number of interesting relationships between the charged matter and electromagnetic flux coming in from the past, and the charged matter and electromagnetic flux going out through the future. And then we took, and we did, well, I didn't really do it, but I quoted the results, that if you do a careful canonical analysis and ask, what does this charge generate? It generates a symmetry, and the symmetry is nothing other than gauge transformations. And this is actually a quantum commutator. I could have been doing Dirac brackets, everything is classical, but then I had to put the eyes in later when I wanted to talk about quantum stuff. This generates the so-called soft part of the charge generates the inhomogeneous transformation on the gauge field A, and the hard part of the charge generates the requisite gauge transformation on any charged matter field. So we associated a symmetry with an infinite number of symmetries with this infinite number of conservation laws.
So, sorry, I missed it. It's not the same charge operator which does this two things?
No, it is, but it has two terms. Sort of a soft term that involves the gauge field and is linear in the gauge field and generates this inhomogeneous term.
Okay. Yeah.
And a hard part which generates the transformations on the matter field. And we exploited the fact that we're working up on scribe plus where everything is free fields. So these are exact formulas which nevertheless apply to any fully interacting quantum field theory. Not quite non-perturbative because there are corrections coming from magnetic monopoles, which is another lecture, which has been worked out as another lecture, but there's a non-perturbative version of these formulas. Okay, so that's what we did last time. That is not how the subject developed. It's in fact kind of the reverse of how this was developed. The way this was discovered was a sort of less rigorous, but nevertheless very useful approach, and that is through the studies of asymptotic symmetries. The first really non-trivial example of it was the analysis analyses are a little bit, it's a little bit more of an art than a science, because you have to start out by making some assumptions about boundary conditions and pull-offs and so on, which you tend to justify at posteriori. Whereas that's why I didn't present it that way, but it's a sort of quicker, dirty way of getting to the answer. So how does this work? Well, we're working in coordinates. We wanted to describe asymptotia. We want to work in retarded coordinates, where u is retarded time on scribe plus, which is at r is infinity. And this is, we wrote it last time, the unit metric on the two-sphere. This is just the flat Minkowski metric. And now, you want to ask the question, how should the various components of the gauge field, how would you expect them to pull off at infinity? Well, in order to have a finite local energy flux, TUU is 1 over r squared gamma z bar. That would be the energy density, energy flux, FU z bar. You want that to go like 1 over r squared. So, because you're going to integrate over a sphere, so you want the instantaneous energy flux to be finite. So you expect FUZ to be order 1. And similarly, FUR and FCR, you want them, this is like the electric field, you want that to go like 1 over r squared for finiteness of energy. And that is consistent with, but doesn't exactly imply, and this is the kind of logic that Braun and Hanot used and BMS used, that AZ should be a order 1. FUZ is a order 1. And AR should be a order 1 over r squared. And AU should be, because we take an r derivative of it, should be a order 1 over r. Now, so this is the way these arguments are made. And
so we know FUR and FCR should go like 1 over r squared. How did that happen?
Let me see if I can remember why the FCR, because you mean why couldn't it go like 1 over r?
Yeah. So we use some stress energy tensor, has 2 of them, or there are r squares somewhere else. Sorry, just.
It's something pretty simple. Let's see.
It's okay.
Yeah.
So it goes like that, and then they make the further.
Well, okay. Now here's the interesting thing. There's a long history of this gravity, gravitational system, and everything, but nobody ever applied this to electromagnetism. So this is what happens if you apply to electromagnetism, or.
I think it should go to like 1 over r squared because there's a cross upper metric between r and u. Is that right? FUZ and FR is in squaring f, in getting f squared, there's a term which is FUZ, FRZ. So that's one, then there should be 1 over r squared.
I see. Okay.
Yeah.
I see. Okay. Thank you. I was missing that. Sorry. Okay. And Andy, this statement that AZ goes like this and so on, that's depends also on some choice of gauge, right? I mean.
Well, okay. So that's why this is an art rather than a science. Okay, and people try to justify this, and why don't you? We can certainly. You don't want to. The logic that the words that people would say, is you want to make the boundary conditions as strong as you can without ruling out any interesting physics. Actually, there's been some, I think that whole story needs to be revisited, and these boundary conditions, we're going to come to some interesting conclusion, but these boundary conditions are actually too strong, and you can learn interesting things by relaxing them. And in fact, I'm not going to discuss this at all, but there's been some beautiful work by Pigliolata and Pujian Mao and who's his collaborator, I forget, in which they actually look at things where the gauge field grows faster. And we did something related in higher dimensions, but subleading soft theorems and subleading symmetries. People are talking about gauge transformations that actually grow at infinity, and then you can do subtraction and still construct a finite charge. It's a very beautiful and intricate story, but I'm not. So these things always make you a little nervous when you hear them. And there's even a story like this in ADS3, which people like Grumiller and various people have been talking about recently, in which if you can relax the Brown-Hano boundary condition without, and I think this is a correct story. I don't fully understand all the implications of it.
I think they claim that that's not the most general follow-ups that can have, and the Brown-Hano condition was too strong.
That the Brown-Hano condition was too strong. If you weaken it, you get a current algebra, and the usual Brown-Hano stress tensor is sort of a Sugawara construction out of that current. I haven't gone through these papers with a fine-tooth comb, but it's a growing story. But anyway, I'm just going to do the simplest. That's why I didn't present it in this way, but it still has always proven to be the fastest way to get the answer.
Can't you just examine propagators, see how they fall off at infinity, and then figure out your boundary condition from there?
Propagators in what gauge?
Yes. Let's say we work in Feynman gauge.
With what boundary condition?
Continue from Euclidean space. Feynman propagators. The things we use for scattering.
Well, the things you use for scattering.
You want to reproduce in the end scattering. So those propagators know everything about the boundary condition. Maybe there's a gauge.
Yes. So that is very subtle. That is very subtle. And I believe that the subleading soft theorems the consistency between everything I'm going to tell you is totally consistent with the Feynman diagram scattering is kind of the thing we understand the best.
Yes.
And everything I'm going to tell you is consistent with that. And Feynman diagram scattering theorem gives you subleading soft theorems. Those are related. People have recently shown to actual weaker boundary conditions that.
So maybe the propagators just a bit have weaker boundary conditions.
Yeah. Okay. I don't know the answers to all these questions. Anyway, this is the cheapest and fastest way to get the answer, and it turns out to be right. By the way, there were also more things I could have matched at infinity. Further subleading, we could have a discussion about further subleading terms in the geometry. Do they match at infinity? Can I get more charges that way? So there's an isomorphic discussion in terms of charges. So I'm not telling you everything, but I'm telling you everything I am telling you is correct. But there's a large space of surrounding things that
But I'm also correct.
that are also correct, but we're not sure which they are. Okay, so now if we just look at this, we say, how do we preserve this condition? actually we preserve this condition by, if we take epsilon to be an arbitrary function of z and v bar. In other words, du epsilon equals 0. That preserves everything I've written here. So these are the large gauge symmetries. And so this is what BMS did for gravity and how they discovered the supertranslations.
So the last condition is the du of epsilon.
Du is epsilon 0, which I need in order to preserve this.
You're saying you're allowing gauge transformations that behave like that.
I'm positing these as my boundary condition.
And that allows these gauge transformations.
And that allows these gauge transformations.
And do you mean that epsilon as r goes to infinity becomes a function of z bar alone, or just for simplicity?
The leading term. Yeah, the leading term. The leading term. Plus order 1 over r. So this is exactly what BMS did. It's just that it's gravity. There's more indices, and it's, 2 or 3 lines, but not. Okay. What do I want to do? Okay, so far, I guess my next order of business then is to relate this to the right. So then we could have proceeded in a different route instead of using charge conservation. We could have said, okay, we have a symmetry. We would still have to know that it was non-trivial, right? So we still consider it being trivial. But then you can draw a Ward identity of the symmetry, and if it gives you a non-trivial relationship between S matrix elements, we know that it's a non-trivial symmetry.
Just the fact that it depends on what's going out makes it clear it's not trivial. The charges change depending on how much, or which charge particles are going out where.
Oh, right. From what I said yesterday, it's completely clear it's
Yes.
non-trivial. But from these 3 lines here, you'd have to do more work before you were sure that you had something non-trivial.
Yes.
What they would, different people would have answered that in different ways, but one of the answer would be construct the charge that generates the symmetry and see if it vanishes or not. But we just started there.
Yeah.
Okay, so now we have a Ward identity. And the Ward identity says that this charge commutes with the Hamiltonian. In terms of the S matrix, it says that if we take any out state, so let's say we have some S matrix element out as in, so then we can take out Q plus epsilon for any Q, S, minus S, Q minus epsilon, in, and that should be equal to 0. So this is the infinitesimal version of the statement that, it's the statement that the charge commutes with the Hamiltonian, S being the exponential of the Hamiltonian, and Q plus epsilon and Q minus epsilon are the same thing. The superscript just denotes the fact that here I'm writing it in a manner that's appropriate for acting on in states, and here I'm writing it in a manner that's appropriate on out states. And what is that? Well, to rewrite some formulas from yesterday, I can write this as there's a soft part on in. There was a soft part, which is minus 2. We had an integral over boundary of scry, dz bar epsilon large had two pieces, a soft piece and a hard piece. And I'm putting the minus here because I'm looking at instates on scry minus. And so this guy, dzn, recall, was the zero mode with some factor, integral over scry minus at fixed z of fvz dv. So this is some kind of zero mode of the gauge field with polarization dz bar epsilon. That's the first term. And then we have a second term, which is the hard part. And the hard part gives us, let's say that we have m incoming particles. So then we get minus the sum from k equals 1 to m of q k in evaluated. That's the charge. Q k in is the charge of the kth hard particle times the function epsilon evaluated at the point zk, where, so here we have Minkowski space, and the kth particle comes in on this sphere, so-called celestial sphere, at the point zk, acting on the instate. So I'm assuming that the instate, the hard part of the instate, is described by m charged particles which enter at this point.
So the first term, the tech is integrated over just the sphere, or also
Integrated over just the sphere.
what about the coordinate on by minus?
Yeah, so we used the fact that it was the integral of fvz, sorry, advanced time dv, and then we had the leading component of av is 0, so this just becomes integral dv dv, and then that becomes az. We can do that integral at scry minus plus, scry minus, the difference between its value at scry minus plus and scry minus minus. And then we use the fact that this had better be pure gauge to write it in terms of this scalar.
That n was the difference between.
Yeah, n was the difference. These are the boundary fields.
Thanks.
So this is a zero mode of the gauge field, but because I constructed it from the field strength, there's a secret factor of omega in there with dv. There's a factor of omega. And
sorry, here the second term, epsilon. So the 2k bar, that's zk bar is where the kth particle hits the celeste.
yeah. So this would just be, if epsilon were constant, this would just be, give us the total charge, right? And this term would vanish.
And your epsilon, was it also a function of v?
No,
You've chosen it to be.
I've chosen it not to be a function of v. And the boundary condition that I
yes,
wrote
right.
down would allow that. We could look in more general, but I think that the other ones in which epsilon depends on v and other gauges don't give new word identities.
Sorry.
Yeah.
What about the term where you have epsilon differentiated with z and n differentiated with z bar?
So that's the two. Integrate by parts and they're equal. And that is very important, that too. That too took us 6 months to sort out because the whole thing seemed wrong without that too. And it's important that this is a scalar field. All right. Now, before I go on, so I'm going to demonstrate the soft theorem, but let me just rewrite, this is true for every epsilon. So in particular, I can take a particular choice of epsilon equals 1 over z minus w. And then this becomes a delta function.
W is a parameter.
Wait, sorry. I didn't write down the word identity. I've just defined q epsilon minus on in, and then there's a similar formula on out. And if I put it together, what I learn is that minus 2 integral d squared z, dz bar epsilon out dzn s minus s dzn minus in, that's the difference between these two terms, is equal to the sum over incoming particles k equals 1 to m qk epsilon k of zk z bar k minus the sum over incoming particles, I guess I used n, these are incoming particles, so I should really put ins here, ins, and then k equals 1 to n of qk out epsilon k of zk out z bar k out times all times the original out s in. Okay, so this is a word identity now for this symmetry, and
But n, if I call it n plus or something just for uniformity,
maybe I should put an n plus up there, but
it's a different function, right, from n minus.
one involves an integral over scribe plus,
Right.
and the other one involves an integral over scribe minus. All right, so for every function epsilon, this, and any scattering amplitude, this, take any scattering amplitude, you multiply it by this number, and you get another scattering amplitude. That number's called the Sawfig.
And sorry, one more question. There's only one epsilon, right? So all the epsilon cases are different functions or the same function?
Same function.
What? Yeah, sorry, there shouldn't.
Oh, thanks.
Thank you. There shouldn't be a K up there. All right. So now, before I go on, let me just make the following tantalizing observation, which I won't really have time to develop. But let me just consider the special case of epsilon 1 over z minus w.
Where W is just some parameter. It's an arbitrary parameter.
Yeah. Then this becomes a delta function because dz bar epsilon is 2 pi delta squared z minus w. So this whole thing collapses to a delta function, and I get that minus 4 pi out dwn s minus s dwn minus is equal to n is equal to the sum over k of qk over z minus over w minus zk minus a similar term, so it'd be qk in minus a similar sum over the out stuff, writing qk out over insertion here in the S matrix, which we can think is a kind of correlation function on the sphere at infinity. The Lorentz group, which is SL2C, acts like the conformal group on that sphere. And so everything looks like a two-dimensional conformal field theory on a sphere. And now we're putting in, we can think of this as the Kac-Moody current, U1 Kac-Moody current. And then this is the Ward identity. Every time it comes near an operator with some charge, you get a pole that's singular at the location of the operator, and the coefficient of the pole is the charge of the operator.
So each particle going in or out is an insertion inside you.
Right. So you think, the idea is to think of scattering as kind of a correlation function on the celestial sphere, and you have a bunch of insertions, ingoing, outgoing particles. That's your rewriting of your scattering amplitude. Lorentz invariance says that that's these collection of this. If you rewrite the scattering amplitude in this way, it has the global conformal symmetry, and then when you put in these, adding a soft photon is the same as inserting. The addition of a soft photon into the S matrix element is the same as in two-dimensional conformal field theory inserting a U1 Kac-Moody current. Now, this is the global conformal group. The nice thing that happens, which we'll discuss a little bit tomorrow, is that in gravity, up to some questions about anomalies at one loop, you get the local conformal group. So this is kind of the picture of what a holographic description of scattering in Minkowski space could potentially be provided by some sort of two-dimensional conformal field theory on a sphere.
Are n plus and n minus the same or different operators in this correlation function?
It's an insertion of their difference. The thing that acts like the thing that acts like a current is an insertion of their difference.
And the ordering here doesn't matter somehow.
Okay, so it turns out that if they're that these two terms are actually equal, if there are no magnetic charges. When there are magnetic charges, you have to be very careful. It gets complexified, and something else interesting happens. But okay.
So equal up to is it?
Equal up to a
N is equal to
yeah.
n.
Yeah. Well, I think maybe it's minus n. It's not zero.
Yeah.
There's only one copy of the U1 Kac-Moody algebra, or is it like U1 cross U1?
There, it turns out that there's a second one that comes from the field C, which we talked about. The derivative of the Goldstone boson. Okay, this is not the lecture I was talking about, but this current has no level with itself. The derivative of the Goldstone boson, which we call the Skeck current, has an off-diagonal level with this. And the Skeck current itself has a level which is the cusp anomalous dimension. So there's an interesting conformal field theory structure there. Okay. All right, yes, so I need to show, this was a little aside, but let me now just,
I'm sorry, and in this, you said this in ICTS, but in this CFD now, on the celestial sphere, every particle is labeled, there's a charge which corresponds to the momentum, magnitude of the momentum of every particle. Is that right? Outer incoming.
well, you could label the insertions. You have choice of bases. you could label the insertions by, for a massless particle, you could label it by the point it arrives at the sphere and the energy. That is actually not the best thing to do. And it's not the best thing to do because it's not what we do in conformal field theory. We would label it by its SL2C weight, right? That is not what we would usually do. We would want to work in terms of asymptotic states, which were highest weight representations of SL2C. And in fact, Shuhong Shao and Sabrina Pistersky and I just wrote a paper working out these highest weight representations just from massive scalars, and you find that then the 3-point functions look like 1 over z1 minus z2 to the h1 plus h2 minus h3, dot, dot, dot. And we've also worked out the simplest case for n equals 4 Yang nulls too. So really starts to look just exactly like conventional conformal field theory, although you get things like imaginary and continuous conformaloids. All right. So let me now.
So is there a central charge?
That turns out to be, the answer is I don't know. Somebody here is working, that's related to double soft limits, and there's an anomaly at one loop, and so there are several issues that need to be sorted out there. What I think we are close to sorting out is the related and simpler question of what the levels of the Kac-Moody, the central charge in the current algebras are, just for QE. So that thing, I think we have understood, but whether or not there's a central charge for the stress tensor, I don't know.
But in the end, you think for QED, this does behave like a free boson, even for OPs with itself.
Yes, but there's a matrix, right? So there's a matrix, right?
There are many free bosons.
First of all, everything gets complexified, and I have DZN, and then I have this get current as DZC of the field that I called C yesterday, the symbolic partner of this time, and so we have DWN and DWC, and we have a 0 here. We have a 1 over Z minus W squared here, and then we have a gamma cusp over Z minus W squared here. That's what
This is the matrix, you're writing the matrix of...
I'm writing the matrix of the OPEs.
And then you can diagonalize this.
Yes, you can diagonalize 2 by 2 matrices.
So it's K and minus K or something.
Well, the eigenvalues are a little funny. I don't quite know what to make of it. They're not anything. Yeah. And we're not sure about all our normalization. Okay. So,
Sorry, but just to understand, so then this now would allow you to understand multiple soft insertions for QED.
right, so we think that multiple soft insertions, we think we computed the complete
Soft bottom, yes.
complete soft S matrix from two-dimensional current algebra.
And you were saying this to me yesterday, but just to confirm, that's just the correlators of free bosons.
It's just the correlators of free bosons.
Why is it free? Somewhere I missed. Why is it free boson? I mean, I know that N. You mean N and C together in this? I missed it. Sorry.
Because why is everything free? It's because we're on scribe plus where nothing interacts. It's just quadratic interactions. The symplectic form just becomes quadratic. There's no.
So it's free in the sense of this kind of a matrix structure.
No, you can compute the commutators in an arbitrary interacting field theory in the limit where the fields are taken to scribe plus. Exactly.
If you've got U1 current algebra, can't you always bosonize the current?
Yeah, it's morally like that, right? You can have a very complicated, what we're doing is morally just like that. You can have a very complicated, this is repeating some things I was telling Shiraz, this, but you can have an arbitrarily complicated two-dimensional conformal field theory with a U1 current or some collection of currents. Then you can write every operator. You can strip off the current algebra piece, and the correlation function factorizes. It's not a local factorization. It factorizes into a current algebra piece times a hard piece. Okay. There's something called the soft factorization theorem in abelian gauge theory, which has been proven in the last 10 years, that the S matrix for abelian gauge theory factorizes into a soft part and hard part. And the soft part has been computed exactly, but the way it's usually done is scheme dependent, because you have to put in a cutoff between what's hard and what's soft. This conformal field theory structure gives us a very natural scheme for dividing
This is
a
what
hard
it
and
shows
soft.
even space-time dimension that they come in. If you give us a 2 plus 1 dimensions, then the photon doesn't factorize at all.
I don't know. I'm in 4 dimensions.
Right,
Soft
okay.
factors, yeah. I would think.
I mean, this is because the scaling dimension, well, it's related to the fact the electric charge is dimensionless, so the scaling dimension of the photon is protected, and it sort of makes 2. But in other dimensions, it's not protected. Then we don't have free photons at infinity.
Right.
You know,
That's probably right. Yeah. Yeah. That's probably right.
I mean, I think also, I was very confused when people like Nima talk about S matrices for super Yang-Mills. What does that mean? Well, you can define it for certain operators that have protected dimensions, but not generally for super Yang-Mills in 3 plus 1 dimension.
Right. Well, there is no S matrix for non-abelian gauge theories in 4 dimensions because of.
But if they're computing something, these guys will do all this.
Right.
All
So,
they're computing.
they're computing the integrand
I see.
of the scattering amplitudes, and the integrals are divergent, and there's no prescription for.
So you can extend this to super Yang-Mills, what you're doing.
You can extend it to super Yang-Mills. The divergence is. It is, in my view, an outstanding problem. And it's a very weird situation that n equals 4 Yang-Mills seems to have this beautiful structure, but we don't know what it is a beautiful structure of, as there isn't an S matrix, right? There's no S matrix in n equals 4 Yang-Mills. So all this beautiful symmetries describe this is in Minkowski space. There's a different story if you're working on a sphere where you have an infrared cutoff. But the beautiful structure of the amplitudes that people talk about is about Minkowskian amplitudes, not amplitudes on the sphere. So there is undoubtedly some beautiful story there, but what is it a beautiful story of? It should be some beautiful story about the S matrix, but we don't know what the S matrix is. So one of my hopes is that an understanding of this symmetry will enable us to give a proper formulation of what an S matrix is, a replacement of, or a generalization of an S matrix for n equals 4 Yang-Mills. And the starting point is there. The problem with the infrared divergences occur only in one loop, and there is a tree level soft gluon theorem, and instead of a U1 Kac-Moody algebra, you get a Kac-Moody algebra with gauge group G, where G is the Yang-Mills group, and then there is a correction to that, but it's not a wild uncontrolled correction. It's a one loop exact correction. So it means something, but I don't know what.
This is the BDS.
What?
This infrared divergence is being one loop exact is BDS, right?
I don't know. Burn. This B burn.
Yeah, burn reasons spin off and spin off. Yes.
Yeah. Similar story in gravity. The correction to the subleading soft theorem that gives the conformal invariance of this element also has something which is one loop exact. Though so many different directions discussed with that there's also been some progress on it.
So that's probably dimensional analysis, right? That gravity thing. That's less surprising.
Is it less surprising in gravity? They somehow they think it's the same statement.
Really? I mean, N equals 4 is really surprising because conformals you might,
Right. Why don't you get corrections in it?
Yeah.
Yeah. So in a way, this thing could be thought of, it's a correction to it's an anomaly in a gauged symmetry, and those are controlled by consistency conditions. So
And what is the gauge symmetry that is an anomaly? Your gauge.
large gauge transformation. Okay. Oops, I went over the line. Sorry, gentlemen. Okay. So now what I'm going to do, all right, so let me just point out that this has now very much the form of the soft photon theorem. I think we're not going to go through all the details here. But here I've got a soft photon, right? These DWNs are soft photons. And here I've got a number times the original S matrix. And moreover, that we can see the collinear poles. Whenever the direction of the soft photon approaches one of the points on the sphere, we get these poles. So it's looking very much like the soft photon. Okay. So let me now just say a few words about the soft photon theorem and how it's traditionally derived. So here's the picture. You have some scattering amplitude, and you've got some incoming and some outgoing particles. And now you want to consider the same scattering amplitude with the addition of one photon. Let's take it to be an outgoing photon with momentum q, and let's call this pk. And we want to consider new scattering amplitude that in the out state has an extra soft photon. Well, let's suppose that we attach, so in order to get that, we have to take this outgoing line, we have to attach it to every external line and also every internal line. We have to sum up over all those things. But let's first look at what happens when we attach it to an external line. Now, in the usual rule for getting scattering amplitudes, first you compute the time-ordered Green function, and then you do the LSZ reduction, which means that you amputate the external legs. So before we added the soft photon, there was no, the scattering amplitude had no term for this. So this would have a propagator which goes like 1 over p squared minus m squared, which of course is equal to infinity because the external particles are on shell. So you amputate those, you don't include those. But once I do this piece squared minus m squared. It's an on-shell photon, so q squared is 0. P squared is equal to m squared. So this just little piece here gives us, I'm not going to keep track of 2's here, we get 1 over pk q. That's the famous pole. That's why this stuff is so important. This amplitude should be a small thing, but somehow it's big, because you're going to get a big factor from a nearly on-shell propagator.
And
That's why you make so many soft photons.
And if I were to think of this physically, I think of this way, that the scattering is happening here, and then you can have something that's emitted, that's nearly on shell, so it goes very, very far away, and then emits a soft photon, and as you go, the photon softer and softer, it go arbitrarily far. And that's the divergence.
Yes, that's the divergence, right? Okay. Now, there's also a vertex factor here, and the vertex factor, of course, well, it's a mu. If we were doing a scalar field, it would be something like a mu phi star d mu phi. And so this a mu is and then there's a factor of the charge. So we'll get a factor of the charge here, which I'm calling qk times e. And then we get, this becomes the polarization, epsilon, contracted into this, which is just the momentum of the K particle. So from this way of attaching, we get a factor like this. And so, but now we have to sum over all such things. And so you get a soft factor that looks like, you get a pole from this, which looks like E qk photon polarization dotted into pk over q dot pk. And but what about, suppose I have some internal line here, and I attach the internal line. Well, the point is the internal lines don't go on shell. I mean, to prove this statement, okay, that's a lot of work. But the basic thing is that the internal lines don't go on shell, so you never get a pole. You can never get a pole in Q from this.
It's sort of measure zero information.
It's measure zero. Okay, you have to be careful about what that statement means.
Yes.
But it really does turn out to be measure zero, and this is the whole answer for the pole. Now, there's a much more subtle analysis for the subleading term, but there's also a universality in the subleading term.
But just to understand that, is that also entirely associated with the propagator, the external propagator, the subleading? Presumably it has nothing to do with what's.
Yeah.
So what is roughly the nature of that more subtle analysis? I mean, just approximately. What have you missed in this analysis?
In the subleading?
You-
I haven't
you give us
computed the subleading term.
But is it just expanding what you've already written down to subleading order or something else?
Well, okay, so if we're talking about QED,
Yes.
then it's just expanding this. But you also have to worry, it can be corrected by, the subleading term QED can be corrected by higher dimension operators. It can't be, interestingly, in gravity.
Just what does that mean? These high dimension operators?
If I change the coupling,
So the vertex factor.
the vertex factor,
It will change.
there's some list of higher dimension operators which Henrietta Elving basically classified all of them. And the subleading in QED can be corrected, but not in gravity.
Okay, but that's just about the amplitude for emission of a photon from it. It's just the vertex corrections. That's all you have to do.
Right.
So the subleading part is the order 1, right? It won't diverge with Q.
Right.
But even the case in which the Q is leaving from the internal line is not is order 1, right? In general.
Okay. The subleading story is a very complex story. it's, let me not, let me not get into all this other terms. An interesting one, but complicated. Okay. So if we add a soft photon, so that's the statement is that if we take the original S matrix and we add a soft photon, S A dagger, let's add it to the initial state, we get the original S matrix times this soft factor. Okay, that's the soft photon theorem. So now we want to turn that into, it looks very much like relationships I was writing on the board. What do you have to do to show that they're exactly the same relation? Well, the big glaring difference is here everything is written in terms of plane waves. And there I was writing things in terms of points on the sphere at infinity. And there's a very explicit relationship between those things. So, in particular, I can write, say, Q. So if I have a photon with momentum Q, it exits at some point Z. I have to do a coordinate transformation at some point Z. So Q will be equal to omega times 1 in terms of that point. So Q0, Q1, Q2, Q3 are omega Z plus Z bar over 1 plus Z bar I Z minus Z bar over 1 plus Z bar and 1 minus Z bar over 1 plus Z bar. So you can check that this is a null vector. Okay, you do all the coordinate transformations. That's what happened. So we can transform the Q's. We can do the same thing for the P's. We can transform everything into points on the sphere of infinity. And then there's a tricky part of understanding. There's some interesting factors in the relationship between, it's sort of intuitively obvious that there should be a relationship between a creation operator. So we had operators like the soft photon operator that creates a soft photon at a point Z on the sphere at null infinity. Okay, that's a mode of the field. It's an integral of the field. We can expand the field in terms of standard plane wave creation and annihilation operators. And it's intuitively obvious that a soft photon located at Z should be a limit. Writing the field operator that acts here should be a soft limit of hard plane wave operators that are pointed, whose momenta are pointed towards Z via this relationship. And there's some factors of 1 over R, 2 pi, and so on. And you can show that explicitly. I won't go through it. But at the end of the day, you find that this Weinberg soft photon theorem, when you rewrite it in the variables we were using, is just identical down to every last 2 pi as the Ward identity that we got, or it's the matrix element of the conservation law relating incoming and outgoing.
So this E vector soft gets related to your N field, I guess.
Right. It gets related to, right, this becomes the
second wave as omega goes to 0 becomes pure gauge. This is just locally it's just a constant shifting. A is equal to constant.
Yes, but it's not a trivial
I
pure gauge.
yeah.
Sorry.
It isn't 0 when you insert it in the. And that's the other, see this pole, see there's a pole here as the energy goes to 0. So it's natural to multiply this by omega so that there's no pole when the energy goes to 0. And multiply this side by omega. And then you might think that this was going to be trivial.
That is the statement that looks like pure.
What?
That's probably the statement that it looks like pure gauge.
That it looks like pure gauge, right? But because of the pole, it doesn't decouple. It's a physical object. Yeah.
So in a celestial sphere, what has the information of the polarization? That's not, I guess.
This is the polarization
Yeah, so,
on the left-hand side.
yeah, on the other side.
This is a soft photon
Uh,
of the same polarization.
no, sorry, on the other side, like, when you write it in terms of ZZ bar, the news tensor and all that.
Ends. He's asking why are there two ends? One for each polarization.
Yes, so it would be that way.
AC and AC bar were both DC and DC bar.
Is this what you're asking me? This is the polarization dc bar epsilon. Okay, so it turns out, and this is a surprising fact, that soft photons are not labeled by their polarization. They're only labeled by the direction from which you, and this is that same factor of 2 that you asked me about 20 minutes ago. That they're only labeled by the direction from which you that you let the momentum go to 0. So they're labeled by points. It's a function on the sphere, not two functions on the sphere. So you might think that you've got one symmetry for every direction of photon and for every polarization. That's,
And it's like a pure gauge.
It's pure gauge. It's labeled by scalar
It's
function.
like a scalar.
but there is a combination
definite.
of them that is pure gauge, of the different polarizations that is pure gauge, and decouples when there are more negative charges. When you have more negative charges, those become independent again, and then you do get a complex. But this is the soft photon theorem without magnetic charges.
I didn't understand. I thought it would be just simpler that this photon is pure gauge, and so the two different polarizations are related by being derivatives of the same thing, and that thing is your end.
And n becomes complex when there are magnetic charges.
So that
How did I know? Why was n real? N was real because I said that f z bar at triplet, which is true, that if you look at the magnetic field out here in a theory with no magnetic monopoles, it will be 0. And therefore, n had better be real. Okay? But if we write az equals dzn, we can always do that. But only if n is real, this is pure gauge. So n becomes complex, fz bar becomes non-zero, and they're twice as many degrees of freedom.
Cube, we take an initial cube and we take it to 0 at the final state. So it can be done in various ways. So they're in various cubes. So why don't we take a sum for all such cubes?
Well, we have one symmetry. Why don't we take a sum over all such cubes? I mean, we have one symmetry for every direction Q. This is a relationship between amplitudes. It's a symmetry, right? One amplitude is related to another amplitude by some factor. It's a symmetry, okay? And it's a symmetry for every Q. So you might think it was also a symmetry for every Q and for every epsilon, but there's a very subtle linear combination. This thing has a kernel, and there's a subtle linear combination that drops out when there are independent charges.
So is this the same that the soft photons in the electric picture and the soft photons in the magnetic picture are different degrees of freedom? After you do an electric.
Yes. Yes.
And
in this, over here, this C becomes complexifying, and it becomes a boson that lives on a torus whose modular parameter is 4 pi I over E squared plus theta over 2 pi.
And another way of saying it is that the gauge transformations of the electric gauge transformations are just totally distinct from the magnetic gauge transformations.
That's right.
So you have pure gauge electric, pure
That's
gauge
right.
magnetic.
So if you rewrite the theory in magnetic potentials, there's a subgroup of that, which is non-trivial. So you double the symmetries, but they combine together in a beautiful, weird way, so it just amounts to complexifying.
I guess the theta term ends up mattering once you get magnetic.
Yeah, if you have magnetic monopoles.
And this C to Z bar seem to be like momentum variables here. But before, in your discussions, it seemed like Z and Z bar are like real space. Am I to think of some kind of a wave packet instead of, real?
Well, if you have a particle with a massless particle with momentum P, it will end up at some point Z.
Z is the direction.
Z is the direction.
But something that
Z
seems
is-
to belong to momentum space rather than real space. I mean, this Penrose diagram, Z and Z bar were like, one was thinking of epsilon of Z, Z bar. In all that, I was thinking of real space.
But there's a canonical map from momentum space to real space, because if you have a massless particle.
Yeah.
Another way of saying it, actually sort of a simpler formula, is at the point Z where a particle with momentum P lands at infinity in this coordinate system is P1 plus IP2 over P0 plus P3.
It's totally non-local and there's U in momentum, but it's localized.
That is what it is.
Yeah.
Okay, so I guess. So I was worried about the
Yeah.
infinite spread of a monochromatic wave.
Because it's just,
So when
the
it's
Z is just a
spread-
direction.
Okay, let me just say some. I'll finish soon. It's a rough day today.
You don't know half of it. Some people's plans fit.
Oh, that's the fun part. I'm assuming you've been reading from 1:30. Okay, so there's something that's implicit in what I've been saying, but let me make it explicit. So I have a symmetry, and that is the statement that this large gauge symmetry is spontaneously broken. Let me make the statements then explain them. It's spontaneously broken. The vacuum in QED is infinitely degenerate. And the soft photons Now, this is a little bit semantics because people, we sometimes do, this is a new kind of symmetry. And so how you, what exactly you want, words you want to use are a little bit up.
Is the statement that the vacuum is infinitely degenerate, is that easy to define, given that there's no gap in the system?
Yes, because let's say we take a state 0. And so H0 is equal to 0. And, but now let's take any one of these symmetry generators. And H on Q plus epsilon will also be equal to 0 because they commute.
But I thought in general it was hard to count how many states at zero energy there are if there is a continuum reaching down to zero. And it's the problem that leads to the ill-defined Sopitan indices, for instance, in the presence of zero.
Well, it's an interesting question whether you could compute the Witten index of the vacuum. I think it's quite possible in a supersymmetric theory. But maybe one way to say it is these states have different angular momentum. So if you insist on saying that there's a unique vacuum, you will conclude that angular momentum is not conserved. You can have a situation in which, you know, you start out with zero angular momentum, stuff goes out, and you're in the vacuum in the far future, but it has non-zero angle. This angular momentum is not equal to the initial angle. Okay, so I mean, certainly the statement that we certainly can't say that Q plus epsilon annihilates the vacuum. That would contradict the soft theorem. So that would be the basis of the statement that the symmetry is spontaneously broken, except for the case where epsilon is a constant.
Sorry, Andy, I think you said something like this yesterday, but can we quantify the degeneracy in terms of flat connections on the two-sphere?
Right. So in the quantum language, I would say that the different vacua differ by the addition of soft photons. If you add a soft photon to the vacuum, you change the angular momentum, but you don't change the energy. In the classical language, they differ by, they're characterized by different flat connections. It's already a classical story that it's spontaneously broken. And it's a little more clear, oddly, this is an aspect, this is more clear in gravity than it is in gauge theory, because their angular momentum is part of the one of the.
When you say flat connections, you're thinking of gauge fields that are gauge equivalent as distinct.
Yeah, so
Right.
they're distinct.
Different gauge functions.
Yeah, so they're labeled by functions epsilon, a mu.
I mean, that's not the way we, in Chern-Simons theory, when we say flat connections, we mean after gauge.
What?
I would use the word flat connections because you tend to think
They're flat.
they're flat, I agree, but you tend to think the equivalent of them is related by gauge. Normally when I say flat connections, I mean connections up to gauge transformations.
All right, I think the word you would use would be non-trivial flat.
Okay, non-trivial. Okay.
So you have to paste them together and all that other stuff.
Yeah, but these are, I would want to call these non-trivial because I think
Yeah, they're not pure.
they're not pure gauge. Right. And what is the Goldstone boson? Well, we know that Q plus epsilon with this field C is equal to epsilon. So the field C shifts like a Goldstone boson does. That is the definition of a Goldstone symmetry is spontaneously broken, and that C is the Goldstone boson, and that the vacuum is infinitely degenerate. Now, here's a difference. If you have an ordinary global symmetry in 4 dimensions, you get super selection sectors. There's an infinite energy cost if you, say, have just a Mexican hat potential, no gauge symmetry, and you put your field at one angle, there's an infinite energy cost to move the angle. Here, the gauge parameters, if you look at the energy of a bubble of a new vacuum, which has to change everywhere overall space, it takes an infinite energy barrier to moving it everywhere at once in space-time. But here, because the parameters depend on the angle, there's sort of one symmetry for each angle. So in a way, it's like a symmetry. It's more like a spontaneously broken symmetry. It has a kind of 1 + 1 dimensional character rather than a 4-dimensional character. And there are not super selection sectors.
Because it's 1 + 1.
Is it more like 0 + 0?
Something like that. Yeah. Okay, but there are not super selection sectors. So if you start out with some flat connection, even classically, and you have any process, at the end of the day, you have a different flat connection. And that is what the gravitational memory effect measures. The change in it's not a flat connection, it's a flat something else. So there aren't super selection sectors here. So in that sense, it's different from a spontaneously, so it's not quite the usual sort of spontaneously broken global symmetries we have. It's also not like a spontaneously broken gauge symmetry where the degrees of freedom get even. It's kind of a new animal. But anyway, this is the language I'm using to describe.
It's not too different from this spontaneously broken diffeomorphism of XYT. I mean, it's because, your point is that there's no additional spatial direction on which these parameters can depend.
Yeah, the Goldstone sub-zero action in SYK also, because of some similar.
The things depend on space, so there's no additional space on which they can depend, which would give you there's no additional volume. Very much like the 0 + 1 dimension.
Yeah, Juan was trying to relate to that.
Okay.
Well, that might be a good place to stop.
ICTS questions?
Yes. So I wanted to ask whether is it understood how, if you work in a BRST formalism with ghosts and so on, how would we think about these things? The gauge transformations and large gauge transformations and so on. Would you, for example, think of it as a breaking of BRST?
Yes. I think that, these are boundary degrees of freedom. And I think that there could be some, I would imagine that there could be some very nice BRST formalism for describing this and for understanding why there's some non-trivial cohomology, BRST cohomology for these boundary degrees of freedom. I should say that most of the the original sort of BMS work was done in what's called Bondi gauge, which is kind of it's like a synchronous, it's a sort of synchronous gauge adapted to retarded coordinates. And 90% of the papers, 99% of the papers, formulas in the subject use that gauge. I think it's actually, so most of my discussions use that gauge. I think it's actually a bad gauge to be using. There were these nice papers of Campiglia-Lotta where they redid things in harmonic gauge, and a lot of got the same results, I think, in a prettier way. So I think that there is a lot to be learned by trying to analyze this in other formulas. But yes, certainly there should be some kind of boundary BRST cohomology. But I don't know how it works.
More questions, Julius? Mumbai.
Mumbai pressing questions, then we go.
Okay, so tomorrow is 10 o'clock, Andy.
Okay.
If you can make it.